Yes, you're El Chapo guy.
Extradited to the U.S. of A.
Yep.
All right. So real quick, let me go through this for period 7. Cu2O is copper 1 oxide. This must be +1 because there's 2 of them. +2 -2 adds up to 0. This one, PbSO4 and those of you in period 7, I already labeled all the charges and everything, so that's why there's a lot of stuff here. But anyways, Pb must be +4 because there's 2 -2s with the sulfate. So that's lead 4. Remember the charge is the Roman numeral, lead 4, sulfate from table E. Pbs +2 -2 are the charges. Lead 2 is the name of Pb +2. Sulfide because it's S. Remember IDE, so lead 2 sulfide adds up to 0. Cobalt 3 phosphate. Cobalt has a +3. Phosphate -3 from table E, so I only need 1 and 1. So COPO4. What was next? I don't know the order here. Titanium 4 fluoride. So that 4 means Ti is +4. So if Ti is +4 and F is -1, I need 4 -1. So TiF4. 7. Copper 2. It's not number 7. We just numbered them. Copper 2. Cu is +2. Sulfide again is -2 wide. They have to add up to 0. Remember, this is related. The charge and the Roman numeral are the same. +2 -2, so 1 and 1, Cus. And then FeO. Fe must be +2, so that's iron 2. Oxygen's always -2, so 1 and 1. So therefore it's iron 2 oxide. Iron 2 oxide was the name. And then we did this real quick here as another example. This would be iron 3 oxide. If Fe is +3, then you're going to need 2 of those and 3 of those to add up to 0. So that's iron 3 oxide. So period 2, you just heard that like 3 times there. All right. Any questions with this? Okay. So what's the last thing we wrote down? The dot structure?
Electrostatic interactions.
Oh, right. Electrostatic. Let's review that.
Yeah, a little bit.
I don't think, actually, in period 7 we didn't write that down yet, so I'm going to write that quick. All right. So I know you guys have it, but I erased
We just did a 1 and then
this complicated double. Sorry, it's got nothing to do with you guys here. All right. So electrostatic. I know you guys have this already. Interactions. Slash Coulombic, right? Period 7 doesn't have this yet, so I'm going to do this really fast. All right, so what do we write down? Very simple definition, right? Olivia?
Attraction between 2 opposite charges.
Attraction between 2 opposite charges. And what does that mean? What examples have we learned about? What did we write down in our notes the other day? So Coulombic forces, it's a little different, which is funny because Mr. McConnelly is going to be in here for me period 7. He knows all about forces, physics teacher, so he could probably elaborate in period 7, but he's not here. So what did we say? What are the 2 examples? Colin?
nucleus and electrons.
Right, so if you have the positive nucleus, that is attracted to the negative electrons. So in AP Chem, we call that Coulombic force, Coulombic interaction. There's other factors besides just saying an attraction. There's reasons why these attractions are stronger or weaker. We don't need to get into all the details in Regents Chem, but anyways, this is one interaction here. The positive nucleus is pulling in or attracting those electrons. That you can call it electrostatic or Coulombic, either one. All right, doesn't matter. But that's opposite charge. So that's a pretty strong attractive force. Atoms don't just break apart. Right, Adam? Atoms don't break down. All right. Atoms are strong. So anyways, the nucleus has a pretty strong force on electrons. Not all of them, right? The further away the electrons are, the looser they're held by that nucleus, so you can take them away a little bit easier. But anyways, that's one. What was the other one, Colin?
Cation and anion.
Yeah, so if we have a positive cation, that's attracted to a negative anion, and that's what's going on in an ionic bond. So that's an ionic bond when you have positive, negative attraction like Na plus, Cl minus, and salt, right? So NaCl, Na is +1, Cl is -1. So all the stuff we're learning about, how to write the names, how to label the charges, all of it really is to help understand what's going on with ionic bonding. So the cation lost an electron, that's why it's +1, and the anion gained an electron, that's why it's negative, and that attraction is called electrostatic or Coulombic interaction, and that's really strong. We learned in lab ionics are strong. What's the proof? What did we do in lab that proved ionics are stronger than covalent? Thank you. One person remembers, or one person at least volunteered. Melting on that little aluminum can lid. Put it above a can. Okay, candle's not very strong. Okay, it's a very weak flame, but not very hot. But the ones that melted were covalent. The ones that didn't melt were ionic. This is why. Okay, well, actually, all right, ionic. This attraction is real strong. Covalents don't have that. Okay, they don't have that. We're going to talk about that today, hopefully by the end. We'll see. All right, so anyways, I wanted to review that. It's important to know what that word means. Opposite charges attract, and there's other more specifics, but all you need to really remember in Regents is that. Okay. Questions? You missed this, obviously, right? You were feverishly writing it. Okay. All right. So now what I want to talk about is, well, a few things here. We're going to learn how to make sure we learn how to write dot structures correctly. I think we only did one so far. If you flip back in your notes, we did RBF. Right? I use the analogy with Mike in the basketball. Okay. So I want to make sure we go through a couple more of those. And you're going to need table S. What's on table S that we would be looking up? Matt Payne, you with me?
Yeah.
Stay with me, Matt. Electronegativity, right. So let's review. What's an ionic bond? Metal, non-metal. Metal is always written first. Why? Because it has a lower electronegativity. Okay? It's always the same order as the periodic table. Metals are first. Okay? We always read left to right. Right? I mean, that's how we do it in our society, our culture here, at least our country. Read left to right, right? So reading left to right, so that's how we write it. Left to right, metals always come first. Why does an ionic bond form? To become stable, to obtain a full balanced shell. Sometimes that's called complete octet. Very good. So remember that. That's the driving force behind all bonds. Yesterday, I showed you a shortcut over here on the side. Group 1, they all form what ion? Plus 1. Group 2? Plus 2. Remember, we skipped the idiots in the middle. 13? Plus 3. Then it becomes negative. Well, negative and positive. Group 14 is a little squirrely. And the reason for that, stay over here with me. Obviously, period 7, you can't do this. You can just imagine. Carbon and silicon. All right, carbon's a non-metal, silicon's a metalloid, germanium's a metalloid, tin and lead are metals. So the charges start to change here. The two up here tend to be more negative, and these tend to be positive because they're more like metals. Metals like to lose electrons. So anyways, -4, -3, -2, -1, and the reason for that is they gain electrons, they become like noble gases. Over here, they lose electrons, they become like noble gases. So remember that concept there. Ionic bonding is metal, non-metal, but the metal always loses that electron, okay? Always. Why is that again? Why do metals always lose electrons? We wrote this. I'm not writing it again. I'm just reviewing. Let's get an example. Some of you look like you need an example because you're falling asleep on me here. Let's go with lithium fluoride. Oops. Lithium fluoride. Write that down. So again, I'm really kind of hammering on ionic bonding this year, and I'm going to try and reverse the fates of the chemistry students this year. A lot of students get bonding all types of confused in their head. They get ionic, covalent confused. By the end of the year, they don't even know what's what because there's so much material they have to know. So I'm really focusing on you memorizing and understanding what ionic bonding is. So when we get to the rest of it, you can separate it in your head. You're like, all right, I got ionic, we'll put that away. Now I'm going to learn the other stuff. So really trying to make sure you understand. Metal, non-metal. What's the formula here? Lithium fluoride. Go to periodic table. You gotta look up the charges to figure out, do we need a subscript? Do we not need a subscript? This should be easy, automatic at this point, I hope. Someone besides Colin. Trevor. Oh no, that was Nicole, sorry. That would be weird if your hand came out of the back of you. Yeah. LIF, right. LIF. Because Li is +1 on the periodic table, F is -1. So, what am I doing here? I'm using this to review the concept. Why, when this bond is formed, and here's really what's happening. Li and F are reacting to form LiF. Alright? That's technically not actually exactly how to draw it, but that's okay for now. So lithium is giving, I want you to write this, lithium is giving fluorine 1 electron. That's what happens in ionic bonding. They transfer electrons. Metals always lose electrons. Nonmetals always gain. Every time. There's never an exception for that. Metals lose, nonmetals gain. Why? Because they want to be stable. They want a full shell, full valence shell. They want a complete octet. Yeah. That's great. Sounds like you guys got that. But why? What's the other reason?
Non-metals have a stronger electronegativity and they want it more.
Very good. So if they're fighting over electrons, let's say, like a tug-of-war scenario, fluorine is way stronger. Fluorine has a 4.0 for electronegativity. That means it has a very strong attraction for electrons. That's what that number means. Electronegativity is attraction for electrons in a bond. So fluorine, the highest, the strongest, is always going to pull electrons away. What's lithium's electronegativity?
1.0.
1.0. Okay, 1.0. So also, as a result, remember the electron configurations. What is lithium's configuration before it loses that electron? Someone look that up. 2-1, that's easy, it's 3 electrons. So lithium has the configuration 2-1. What's fluorine before it gains that electron?
2-7.
2-7. So now over here, let's write down what their configurations turn into after the transfer of electrons. So lithium becomes
2.
just 2, and fluorine becomes
2-8.
2-8. Everybody's happy. Now, remember, this compound is actually made up of ions. That's why it's called ionic. Li+1, F-1, but we just don't label it. We don't label it in the compound. It's assumed that we know that. All right? So as a result, because it loses 1, it becomes Li+1, right? Li+1, and F becomes -1, and then that's the reason that we're 2 and 2-8. So now lithium has a full shell, full first level like helium. That's 2. And then who's 2-8? What noble gas?
Neon.
Neon. Everything I just went over is on that worksheet. Okay? Some of the part of the worksheet you're going to have to explain this business. Okay? The electron configuration, what noble gas configuration it has, electronegativity, and there is one more part. What is the difference in electronegativity between Li and F? What is the difference? When I say difference, I mean subtract. 3.0, write that down. 3.0 difference in electronegativity. 3.0 difference in electronegativity. There's a reason I'm going over that with you. The larger the difference, the more ionic it is. The larger the difference, the more ionic. So we're going to write that. The larger the difference, the more ionic. The regents will call it ionic character. More ionic, parentheses, character. That just means, bless you, that just means, bless you,
Thanks.
which bond or which compound is a better bond or a better compound. So the larger the difference, the better this bond is, the stronger it is. So the bigger the difference, the stronger it is. So what we're going to do now, I'm going to write 2 compounds on the board. I want you to write the dot structure for them, if you remember how. Try that. Show me the dot structure. Show me the electron configuration after they bond. Okay, you can do it individually, but after they bond, I want the electron configuration. I want you to subtract the electronegativities, and then out of the 2 compounds, based on what we just wrote, tell me which one is more ionic. So everything we just went over, we're going to practice right now, except we're going to throw dot structures in the mix. Okay, we did one the other day. Let's see how you do. So I'll give you a few minutes, then we'll go over it. And there's still that music video I haven't gotten to yet.
I should make a music video.
It's pretty funny. Eventually I'll get to it. Period 7 complains all the time that I don't get to the videos. I never get to videos because I talk too much or whatever. So maybe no video today because I'll talk too much. All right, here we go. Let's go with, okay, I'll give you a sort of easier one. Let's go with calcium, we'll go with the F again. Calcium fluoride, CaF2. I'll just give you the compound. And then we'll go aluminum chloride. So I'll do that one right here. AlCl3. So if you remember how to do the dot structures, great. If not, then do everything else I asked. What's the electron configuration of the aluminum and chloride, the calcium and fluoride after they bond? What's the electron configurations? What noble gas electron configurations do they now have? Subtract their electronegativities. Which one is more ionic? Which one is a more or larger or greater ionic character is how that's worded. And then I'm going to throw one more thing in at the end. But try and do the dot structure first. Remember, these are metals with nonmetals. That's ionic. Positive-negative interaction. Back to your electrostatic, Coulombic. Makes them very strong. I know you're trying to work. Hopefully you can still do that while I'm going on and on here. I feel like the more I say this stuff, it's going to ooze into your brain and just stick in there. Right, Courtney? So remember, actually not remember, we haven't really done a whole lot yet, so let me rephrase that. If you know the formula of the compound, that's how many atoms should be in the dot structure. So CaF2, I need one Ca and two Fs in my dot structure. If I have one Al and three Cls, I need one Al and three Cls in my dot structure. Again, we haven't really done this. I just want to see how we do here. That worksheet, you're practicing more of this. So we'll just go through these two examples and then move on, because the worksheet will practice more, like I said.
What else do you have besides the dot structure?
Dot structure, I want the electron configuration for each ion after it bonded. What noble gas configuration that ion has. Subtract the electronegativities in each compound and tell me which compound is more ionic. Yes, sir.
So would it be like this?
Sort of. I like what I'm seeing so far. The good news is there's some good things. The bad news is no one's done the dot structure right yet.
Is this right?
But again, I haven't really showed you, so I don't blame you.
Oh, wait a minute.
You're getting there. These two, this is not an easy task. I'm asking you to do like 5 things here. Not bad. You just have to add one little thing. what did we learn? I know I keep talking. That's just how I am. What did we learn about the dots and how many bonds it can form? You guys remember that? Based on the dot structure, how many bonds can it form?
Yeah.
You guys remember that? Well, how do we figure that out? So, for example, if I have sulfur, 1, 2, 3, 4, 5, 6, how many bonds can that make?
2.
2. 1, 2, right. So when you're doing these dot structures, you're going to see calcium can form 2 bonds, fluorine can only form 1, aluminum can form 3, chloride can only form 1. So that helps you understand a little bit how to put the dots together. So what you do is you take one dot from one element, one dot from another, put them together. And if you remember, I did something like this, right? So let's say that's how we would show the bond. If you're getting confused with that, that's fine. I'm gonna give you another minute, and then I'm gonna go over all this business, and then whatever time we have left, may not be any.
What was the other thing?
I want if you can't do dot structures, stop trying. Right now, I'll give you another minute. Give me the electron configuration of both of those in the compound, the electron configuration of both of those in the compound, what noble gas configuration that they now have, right? Because it changes once they form a bond. And then I also want you to subtract the electronegativities of each compound, Ca and F, Al and Cl, and then based on your number that you get for the difference there, the subtraction, which one is more ionic, or has what the regents will say, a greater ionic character. So that stuff you can do. Feel good about that. You can do that, even if you can't do the dot structure. So now I'll give you one more minute, and I'll go over everything. Yeah, I'm just gonna. I'll leave it unlocked. I don't think. Well, I know it's Mr. McConnelly, period 7. I'm gonna talk to him. I don't know who's in here, period 8. Oh yeah, period 8 lab. Sorry, it's not gonna be very exciting. I'm just gonna have you work on Regents problems.
How many topics?
That's fine.
But I wrote that you can give them 10 to 15 minutes at the end to hang out. So you work, you guys, I'm sure you'll be fine. So you work for most of the class collected. So this is the regents. I'm just gonna have you work on the multiple choice. Put the answers on a separate paper. I just didn't want you to sit here doing nothing for the whole period. Can't have too much free time, right, Courtney?
Yeah.
All right, here we go. CaF2. How many dots does Ca have? 2. Everybody look up here, please. Whenever we do ionic compounds, we always write the metal first. Whenever we do dot structures, always do the metal first. So Ca, 1, 2. Now fluorine, how many dots? 7. Now, I'm just going to kind of show you the thought process. Don't write down exactly what I'm doing, but this is how I think of it. So I have F with 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I'm going to take one of these F's, and I'm going to put it right here. I'm going to take the other F, and I'm going to put it right there. Because I need 2 dots to overlap, essentially, or 2 dots, 1 dot from calcium, 1 dot from fluorine to pair up. Same thing here, 1 dot from calcium, 1 dot from fluorine, they have to pair up. So I'm going to rewrite this so that they match up, or they pair up, however you want to call it, or whatever you want to say there. So this dot and this dot come from calcium. And now the way I teach it is, I don't use dots here, I use X's just so I know the difference between Ca and F. That's all. A dot and an X are the same thing. So this dot I'm actually going to put here, so there's my one single dot for F, and then all the other ones are paired up. So there's one ionic bond being formed. There's the 7F, 1 from calcium. I'm going to do the same thing here, put the X here. There's my 7 dots for F. There's my 1 for calcium. That's my dot structure for calcium fluoride. There's only one more thing we have to do. This is an ionic bond. Calcium is getting rid of 2 electrons. So you have to show that. Ca is +2. Each F is gaining 1. It's the nonmetal, it takes 1. F is -1. So that's how we do the dot structure. Now I want to look up the electronegativities and do the electron configurations. Hopefully I have time to squeeze that in. Fluorine becomes 2-8 because it gains 1 electron. Calcium loses 2, becomes 2-8-8. Everybody has a full valence shell. Everybody's happy. What noble gas is 2-8? Neon. Who's 2-8-8? Argon. We're almost done. Now we look up the electronegativity. What's calcium's electronegativity? 1. Fluorine is 4. So the difference is 3.0. And that's it. We're done. Now I am going to run out of time, so I'm just going to jump to the end here real quick. So you would do the same thing for AlCl3. Again, I'm out of time. Let's do this real fast. What's the difference in electronegativity? What's Al?
1.6.
1.6. What's Cl?
3.2.
3.2. That's a
1.6.
1.6 difference. Which one is more ionic? This one. There's a bigger difference. Stay with me. Bigger difference between this +2 and that -1. So here's what that really means. Listen, last thing real quick. Calcium is really positive and fluoride is really negative. If you have a really strong positive, really strong negative, that's a really strong attraction. This positive and that negative aren't as strong. So that attraction is going to be weaker. It's a weaker bond. That's what that number means. The bigger the difference, the more opposite they are. The more positive, the more negative. So that's a stronger attraction. That's called more ionic or greater ionic character. So I'm going to have to stop. Bell's going to ring. So you guys will have this worksheet on Monday, period 7. You're getting it right now. But yeah, period 2, you get that on Monday. And have a wonderful weekend. I'll see a few of you later. I think the bus is